Oh yeah, it started right now.
Yeah, so I'll start. Actually, I wanted to show you first. I wanted to show you this. Yeah, this is research. This is research part of my webpage, and yeah, I created this separate blog about just about GT shadows and the action on child's drawings, and you can find many things, including this paper. It's kind of long, and then another paper about the action. There is also a software package. Then there are sessions for working with the package, and then various presentations. So, yeah, another thing, another website, yeah, that we may or may not get to this website is about this database of Belly maps. So let me go back to the slides. And yeah, so it's yeah, this is real new in a sense that some of it is not written. It's kind of in preparation. And it's so, as I wrote here, it's loosely based. This is loosely based on papers in preparation with students, So the topic is actually, yeah, it's see, two of these students were undergraduate students who worked with me, and that's why, I mean, some of the material is really elementary, and the only thing that's kind of beyond typical undergraduate material is profinite. When I talk about profinite groups, profinite completions, otherwise it's many things will be relatively elementary. But then, yeah, then you'll see that the topic touches some stuff that's more advanced, and then it can become very, very advanced. So the motivation for this research is the absolute Galois group of rational numbers, and as everybody knows, this is the group of field automorphisms of the algebraic closure of the field of rational numbers. And this group is uncountable, but well, here is what you can kind of say right away from kind of basic undergraduate algebra or gradient algebra, is that if you have a finite Galois extension and an element of this finite group, then you can always extend it to an element of GQ. In fact, you can do it in infinitely many ways. And the group, well, you probably know this group is one of the most mysterious objects in mathematics. So in 1990, Vladimir Greenfield introduced yet another mysterious group, and he called it GT hat. This group consists of pairs, M hat of hat in this Cartesian product, satisfying some conditions. So typically when I put hat, I mean profinite completion. For example, Z hat here means the profinite completion of Z. And F2 denotes the free group on two generators. So F2 hat denotes the profinite completion of the free group on two generators. So the notation GT hat is a bit misleading, because some people may start thinking that there is a group GT and I'm taking its profinite completion. I'm not doing this. So there's no group like this. But later you'll see that GT hat is a limit of a certain functor into the category of finite groups. So it is known that GT hat receives a one-to-one homomorphism from this absolute Galois group. Yeah, so just to show you how hard it is to work with these objects is we explicitly know only two elements of GQ and GT hat. So namely, we know the complex conjugation, the identity element and the complex conjugation. And these are the corresponding elements in GT hat. So 0, 1 and negative 1, 1. The second component is 1, it's the identity element in F2. Well, F2 hat. Also in F2 hat. So let me also mention that I forgot to mention in the beginning of the talk is that sometimes I'm going to be sloppy about technical details, yeah, I'm going to, hopefully I'll tell you, okay, I'm lying here a little bit, or here or there, but So yeah, so this slide is actually contains a lot of information. So it's I'm basically showing you various incarnations of what is called a child's drawing of degree D. So on the one hand, a child's drawing of degree D is an isomorphism class of a connected bipartite ribbon graph with D edges. So bipartite simply means that I can color edges by black and white. Traditionally, they colored by black and white. And then there are no edges from black to black or white to white. And then a ribbon simply means that it's important how it is drawn. It's in the neighborhood of every. So I'm taking if I look at a subset of edges incident to every vertex, I have to choose a cyclic order. So it's the way it's drawn tells me, okay, so I chose this cyclic order: 1, 2, 3, 4, or 1, 2, 3, 4. Or if I look at the neighborhood of this vertex, 1, 2, 3, 4, or 1, 2, 3, 4. Equivalently, a child's drawing of degree D can be defined as an equivalence class of a pair of permutations in SD symmetric group on D lattice, for which the group generated by G1 and G2 acts transitively on this set. In fact, from now on, I'm going to say, when I say transitive subgroup, I mean a subgroup of SD that acts transitively on 1, 2, T. Equivalently, we can define a child's drawing of degree D as a conjugacy class of an index D subgroup in F2. So I denote by X and Y the generators of the free group on 2 generators. Then, then we can do something else. We can define a child's drawing of degree D as a conjugacy class of a group homomorphism from F2 to SD, with the image being transitive. So here the conjugacy means different things. Here when I have a homomorphism from F2 to SD, I conjugate with elements of SD. So first act by homomorphism, then conjugate. And here, when I'm talking about index D subgroups, I talk about conjugation by elements in F2, by elements of F2. So, and then, so some geometry, equivalently, a child's drawing of degree D can be defined as an isomorphism class of a non-constant holomorphic map phi from a compact connected Riemann surface without boundary. And I assume that this map does not have branch points above every W in a complement of 0, 1, and infinity. So that's what we have. And actually, the third model is the closest. It's the most helpful if I want to define the action of GQ of the absolute Galois group on child's drawings. So given a child's drawing D, we can find a smooth projective curve X defined over the field of rationals and an algebraic map from X to P1 to projective line over Q bar that does not have branch points above every point in this complement, in 0, 1, and infinity. And we say that this pair is X phi is called a belly pair representing D or realizing D. So the coefficients defining the curve and the map lie in some finite Galois extension because I need finitely many coefficients to define the curve and finitely many coefficients to define the map. So I get they lie in some field, a finite field extension. I can take the Galois closure and here you go. So then given an element of this finite group, I can act on a child's drawing by simply acting on coefficients. So I put new in quotation marks, in parentheses. I put new in parentheses because sometimes it's the same, because many belly pairs are actually defined over Q, and then you act and you don't change it. But of course, I mean, the action becomes interesting when the child's drawing is defined, when the abelian pair is defined over a number field different from Q.
Vasily, excuse me.
Yes, I have a question.
Are you gonna tell us how you get, say, a child drawing from a abelian pair?
That's also possible. Yes. So when you have a abelian pair, it's also a Riemann surface, right? X is also, it's because it's a smooth projective curve over Q bar. So in particular, it's a Riemann surface, right? Coming back to this model, Riemann surface. Yeah. So all you need to do is to take this segment. You basically look at CP1, take this segment on the real line from 0 to 1, and take its pre-image. Image. So you'll see a graph embedded into the surface, and that will be that.
And the pre-image of 0 would be white, and
the convention is that pre-image of 0 is traditionally black, and pre-image of 1 is white.
Okay, that's fine. Yeah. Thank you.
So then, so that's, if you look at this child's drawing, I don't remember the number field. It may be actually Q adjoint square root of -1. But when you act by the Galois group, by the absolute Galois group, you just you get the orbit that has only 2 elements. So the second element is represented by this graph. So here are basic invariants. So basic invariants of child's drawings. So the first obvious invariant is, of course, the degree. When you act by GQ, you don't change the degree. This is obvious. So degree of the covering stays the same. Then another invariant is the monodromy group, and the monodromy group is the conjugacy class of the subgroup. Remember this is always a transitive subgroup in SD, and its conjugacy class is invariant. Then here is another important invariant called the passport. So if you represent your child's drawing by a pair of permutations, G1, G2, then you need to form a triple of permutations. So you take G1, G2, and then this permutation, and then you compute a cycle type or cycle structure of each permutation, which is, of course, a partition of D. So a passport is simply a triple of partitions. And yes, so this triple of partitions is called passport, and it's also invariant under the action. And then there are more invariants. There's the cartographic group and more. So I want to mention something that may be called well, it's kind of falls in the category of invariance. So let's say that I have, let me denote by B3 Artin's braid group on 3 strands, and I'm going to denote by sigma 1, sigma 2 the standard generators of B3. Then it turns out that these formulas define an action of B3 on child's drawings. And in fact, PB3 acts trivially. When you look at the formulas, it's not obvious because you think, no, it's not. I mean, if you act, let's say, act by sigma 1 twice, so sigma 1 squared will be already an element of the pure braid group on 3 strands, and it acts. So if you look at the formula, it looks like it acts non-trivially, but then if you remember that we can also, we consider these triples up to permutations, and then it becomes trivial. The action of PB3 becomes trivial. Therefore, we actually have the action of the quotient B3 by PB3. So it's actually S3 acting on child's drawings. Now, if you recently taught complex analysis, then you probably talked about Möbius linear fractional transformations. So there is another way to define this action of S3 by simply, so there is there is a standard homomorphism from S3 to the group of linear fractional transformation of CP1. And if you go back to this model of holomorphic maps, so let's say you have a child's drawing, it is represented by a holomorphic map. You can post-compose it with a linear fractional transformation, and that coming from S3, and this is the action. You get the same action.
S3 is the one which permutes 0, 1, and infinity?
That's right, exactly. So that's why it's obvious that this action of S3 is compatible with the action of GQ. Just because linear fractional transformations has coefficients in Z. So it's therefore in Q. Invariant. I mean, compatible with the action. Two actions commute. Yeah, so that's what I wrote here, that GQ the action of GQ commutes with the action of S3. So now, yeah, let me tell you a little bit more about GT hat. And here is where I'm going to start lying, because I'm not going to talk about GT hat. I'm going to talk about what I call the gentle version of GT hat, which is slightly simpler. And but for the rest of the talk, I'll just call it GT hat, even though it's a version of the original GT hat. So yeah, so let's say that we have this pair M hat F hat, and then these formulas define a continuous homomorphism, continuous endomorphism of F2 hat. And then so then we can use this formula to define a structure of a monoid on this set. So Z hat cross F2 hat is a monoid with respect to this binary operation. And 0, 1 is the identity element of this monoid. Yeah, then I need, so to continue, I need to go deeper, a little bit deeper into braid groups. So B3 is the Artin's braid group. Then I'm going to denote by C the square of this element. X1, 2 will be sigma 1 squared, and X2, 3 is sigma 2 squared. So then, so to define a gentle version, I need this submonoid. So GT mon is the submonoid of Z hat F2 hat that consists of pairs satisfying the hexagon relations. So these are relations in the way I wrote them, the relations in B3 hat, in the profinite completion of B3. And there is another condition that F2 belongs to the topological closure of the commutator subgroup. So yeah, so and then yeah, GT hat gentle is just the gentle version of GT hat is the group of invertible elements of this monoid. That's all. Yeah, of course. I mean, when you look at the definitions, you may think, "Oh, why is it even non-empty? I mean, non-trivial. Do we have a non-trivial element, non-identity element?" Well, the good news is that negative 1, 1 satisfies this condition. I mean, hexagon relations, and of course, 1 belongs to the commutator subgroup. But of course, I mean, you would want to get more, right? So it's not obvious. It's not easy to show that there are more elements, and yeah, for this you do need to use this fact I mentioned in the beginning, that GQ embeds into GT hat, and then inside GQ we have a lot of elements. So that's why we have a lot of them. Therefore, we have uncountably many elements in GT hat.
So what's the reason of talking about the gentle version? Is it Rockworth?
Yeah, I'm going to I'm going to mention that. Yeah, there is a reason. Yeah. So the formula. So first of all, yeah, another thing I wanted to mention is that, yeah, when you look at this formula, it may be somewhat painful because look at, I mean, it's unnatural in my opinion. 2m1, m2 plus m1 plus m2, but things become nice if you replace m1 hat by 2m1 plus 1 and m2 hat by 2m2 hat plus 1, because then this operation simply becomes multiplication, and it turns out that this formula defines a homomorphism, continuous group homomorphism from this gentle version of GT hat to the group of units of Z hat. So I mean, if this profinite business is I mean, if you don't deal it on a regular basis, then maybe I should say that if you take Z, so inside Z we have only two units, -1 and 1. But as soon as you pass to the completion, then you have a lot of units. So this is what we have. And it makes sense to call this chi vir the virtual cyclotomic character, because it's related to the cyclotomic character from the Galois theory. And yeah, so as I said, in the remaining slides, I'll be sloppy, and I'm going to call GT gen GT hat. And so as far as I know, this gentle version was introduced by David Harbater and Leila Schnaps in 2000. And they called it GT0. I mean, the subscript 0 was not was chosen just, well, more or less randomly. But I mean, if you ask David, I think last time I talked to him, he told me that somebody already introduced it before or something like that. So the reason I call it gentle is because because the original version of GT hat is more complicated. So it may be intimidating. It may be intimidating to students, and then so that's why I call it gentle. Okay, it's not that bad. So and then the students don't feel that intimidated, and it's better. So, Sasha, did I answer your question?
Yeah, very good. Thank you.
Yes. So, well, now let me explain how GT hat acts on Child's drawings. I'm going to start with this element. It's a pair, M hat of hat, and a Child's drawing, D. So for the purposes of the action, it's convenient to represent D by a group homomorphism from F2 to SD, where the image is transitive. And so if you compare to finite index subgroups, all you need to do is to just take the stabilizer of 1, or stabilizer of 2, or stabilizer of 3. Because as soon as you have a homomorphism, you have the action of F2 on the set 1, 2, 3 dots D. And all these stabilizers will be conjugate to each other. So you can take any stabilizer; it will represent a Child's drawing. So then, but it's convenient. Yeah, it's convenient to work with this homomorphism to represent the Child's drawing by a homomorphism, and then extend it by continuity to this homomorphism psi hat from F2 hat to SD. So whenever I have a finite group, I consider it with the discrete topology. So on SD there is the discrete topology, and on F2 hat I have the crude topology. Then the Child's drawing. So the new Child's drawing corresponds to the group homomorphism, which is obtained like this. So I take psi hat, precompose it with this endomorphism of F2 hat, and I restrict it to F2. Then I get a homomorphism from F2 to SD. And let me just remind you that these were the formulas for the endomorphism of F2 hat. These were the formulas. So I mean, in principle, it's not obvious. It's not obvious that we get this. I mean, the action of GT hat is compatible with the action of GQ. Remember, we have the embedding, right, from GQ to. In the beginning of the talk, I had this embedding. Let me call it the Ihara embedding. The Ihara embedding, and well, if you ask me, well, what's a good way? What's a good reference? You may start with this paper by Ihara, which is kind of where the embedding is described. But then, yeah, it's not enough. I mean, it's a good idea also to read the appendix by M. Salem and Pierre Lachac and more. And then, so now let me get to GT shadows. So for that, let's get a bit deeper into braid groups. Well, I already said that B3 denotes the Artin braid group on 3 strands. PB3 is the pure braid group. So then sigma 1 can be represented like this by this picture. Sigma 2 can be represented by this picture. It's convenient to denote by delta this element. And then PB3, the pure braid group, is generated by these elements. C2, yes, C2 is simply delta squared. Then it is known that the center of B3 coincides with the center of PB3, and it's the infinite cyclic group generated by C. And then the subgroup, and then X1, 2, X2, 3 generate a free subgroup inside PB3. And in fact, PB3 is just the direct product of F2 and its center. So that's why I'm going to tacitly identify F2 with this subgroup. And sometimes I'm going to denote by X. I'm going to denote by X, X1, 2, and Y will be X2, 3. And yeah, there are also these automorphisms that allow us to write a simpler version of hexagon relations. So for my purposes, I will also need this poset. So this poset will play an important role. So it consists of normal subgroups of finite index inside B3, and each subgroup must sit inside PB3. So PB3, remember, PB3 sits inside B3, and then N sits inside PB3. And we abbreviate. So in many slides, I'm going to just use this abbreviation NFI. NFI. So when I say NFI, I mean this poset. And whenever I have an element in this poset, yeah, I can do 2 things, and it will be also important. I take N and intersect it with F2. Then I get a finite index normal subgroup in F2. Or I can consider cosets of X1, 2, X2, 3, and C. These cosets will be elements of a finite group. So therefore, they will have finite orders. And I can take the least common multiple of all these orders. So given N, I'm going to produce NF2 and this integer, this positive integer, N ord. So they play an important role because here, so if I have a pair MF, an integer and an element NF2, I'm going to say that this pair satisfies hexagon relations modulo N if I have this. So if you see these relations first time, you think, they're highly unnatural. They just fell from the sky. What's going on? So here is a motivation. Here's a motivation, and there are more motivations, but let me mention just one motivation, that if if a pair MF satisfies the hexagon relations modulo N, then these formulas define a group homomorphism from B3 to B3 quotient by N. So in fact, if you look, you have just if you remember, relations of B3 is sigma 1, sigma 2, sigma 1 is sigma 2, sigma 1, sigma 2. So in some sense, you kind of see pieces of that. Pieces of that. When you act, look, if you take sigma 1 and send it here, you get this. If you apply it to sigma 2, you get this. And well, and this is precisely the product, right, of the image of sigma 1, sigma 2. And this is the image of sigma 2, sigma 1. So notice that the choice of NF2 and NORD is important here, because eventually I want to pass to cosets. I don't want to talk about the integer. I want to talk about m, little m mod n ord, and I'm going to talk about little f modulo NF2. So yeah, I want my relations to be defined for cosets. So that's why I'm choosing NF2 and ord appropriately for that. So then it makes sense to take this TMF and restrict it to PB3 and F2, and we get useful things. So we get a homomorphism. When I restrict to PB3, I get a homomorphism from PB3 to this quotient. And if I restrict it to F2, I can get a homomorphism from F2 to this quotient. And in fact, here are explicit formulas for these homomorphisms. And then for TMF F2. Explicit formulas, and they probably remind you the formulas for the endomorphism E, remember E, the endomorphism of F2 hat. So it's not hard to show that TMF is on 2 if and only if this homomorphism is on 2 from here to here, and if and only if this homomorphism is on 2. And yeah, so it turns out that the kernel of TMF coincides with the kernel of this homomorphism. Therefore, the kernel of TMF is actually an element of my poset. And then finally, we can define a GD shadow with a target N. So given N, remember N is a normal subgroup of finite index in B3 that sits inside PB3. And the GD shadow with the target N is a pair like this. So an integer, an element of this quotient ring, right? And this coset satisfying the hexagon relations and the following conditions. So 2m plus 1 should represent the unit in this ring. The coset of F should be in the commutator subgroup, or equivalently, there exists an element. Equivalently, it can be represented by an element in the commutator subgroup of F2. And the third condition is that this homomorphism, or equivalently this homomorphism, or equivalently this homomorphism should be on 2. So that's what I want from GT shadows. And then I'm going to denote by GTN the set of GT shadows with a target N. So yeah, well, guess what? GT shadows form a groupoid. And GT shadows will be morphisms of this groupoid. So the set of objects is this poset. And then given K and N morphisms from K to N are precisely GT shadows with the target N. And the kernel of TMF is K. Should be K. Yeah, so of course, I mean, if you look at this definition, you think, oh, wait a minute, how can we even compose such morphisms? Well, here's an explicit formula. And so let's say that you have a triple of objects. You have 3 objects, and a morphism from here to here, and then another morphism from here to here. Then to compose them, I choose representatives. Yeah, so M1, M2 are integers. And then F1, F2 are elements of F2 representing cosets. And then I write this expression. Yeah, the only thing that's not defined is E. But we had a similar E. And anyway, in the next slide, I'm going to tell you a little bit more about this E. It's actually a pretty explicit endomorphism of F2. Endomorphism of F2. So yeah, if you like, it's just this. It's just MF given MF, and then this formula is defined an endomorphism of F2. And for a pair like this, we have this property. And yeah, one can show actually that Z cross F2 is a monoid with respect to this binary operation, and 0,1 is the identity element of this monoid.
Excuse me, do you remember it right that the slide basically repeats your previous slide?
Yeah, they're similar. Yes.
What's the hats?
Right, without heads. But yeah, as soon as you remove heads, you have to be more careful, because I can't. Yeah, this is rarely an automorphism. This EMF will rarely be an automorphism. But I mean, we need it. I mean, we needed this to define the composition. This formula for the composition. I mean, of course, if you look at this formula, you may have a lot of questions, like why it doesn't depend on the choice of representatives? Well, it can be proved. Why is the composition so given two GT shadows, if we compose them, why do we get a GT shadow, right? Yeah, so all these things can be proved. And yeah, so in principle, if you want a more conceptual explanation for these formulas, it exists. But then I need to switch to the language of operads. So if we switch to the language of operads, then many things become easy. Then I'm just talking about isomorphisms in the category of so isomorphisms of operads in the category of finite groupoids. So it's then isomorphisms can be composed. So that's what I'm doing. But I mean there are talks that I give. Sometimes I give talks using the language of operads. Sometimes I avoid using the language of operads. So here I chose to avoid. Yeah, it's possible that Sasha thinks that it's a bad idea. Why did you avoid it?
Exactly. You read my mind.
Yeah. Well, I mean, yeah, you can watch other videos in that blog on my webpage. So I mean, some of them I use the language of operads.
Sure.
But then again, if you look at this slide, I agree that it's kind of, I mean, it repeats some of the things from the profinite story, but I kind of think of this as auxiliary. It's auxiliary. I mean, if you see some meaning, some deeper meaning here, please let me know. But it's mostly auxiliary. So here are basic facts about this groupoid. So first of all, this groupoid has infinitely many objects. Why? Because the pose set is infinite, because PB3 is residually finite. And then this groupoid is highly disconnected. And that's because, well, if you look at the definition of the morphism, see morphisms from K to N, GT shadows, for which the kernel is K. So as soon as the kernel K, it tells us that quotients will be isomorphic. So B3 quotient by K will be isomorphic to B3 quotient by N. So if the quotients are not isomorphic, for example, they may have different orders, different indices, then that's all. Then there are no morphisms. There are no morphisms, so this groupoid is highly disconnected. However, for every n, the connected component of n is a finite groupoid. In fact, in many examples, this groupoid is actually a group. I have only one object. In many examples, just one object. And if I have only one object, then I'm going to say that n is isolated. N is isolated. So if the connected component of n has only one object, in other words, GTN is a group, then I'm going to say that n is isolated. And then another thing that can be proved relatively easy is that for every n in NFI, because the groupoid, the connected component is finite, I can take finitely many objects, intersect them, and the object I get will be isolated. And in particular, the subpose set of isolated elements is cofinal. So in other words, if you take any element in NFI, you can always take a subset, a subgroup inside that n that is isolated. So yeah, when you look at this, I mean, yeah, if you recently taught Galois theory, yeah, even at undergraduate level, I mean, it's just, yeah, when we teach Galois theory, we do not introduce groupoids, right? We talk about groups, but it is possible. It is possible because look, if you look at finite field extensions that are not Galois, then you can look at, let's say your base field is F. Then you can look at, instead of looking at automorphisms, you can look at F isomorphisms from one extension to another. So here is your groupoid, right? And then you take the Galois closure. Well, here is your isolated element. So that's the analogy. So it's important, yeah, it's important to talk about the situation when I have n sitting inside H. Well, just because I have the poset structure, it plays a role. So let's say that I have n and H, and n sits inside H. Then of course n of 2 will sit inside H of 2. And then the corresponding integer will divide and H or ord will divide n ord. And then it's relatively easy to see that given a pair that represents a GT shadow with a target n, the same pair will also represent a GT shadow with the target H. Hence, we have a natural map, kind of reduction modulo H from GTN to GTH. Moreover, if n and H are isolated, so it means that GTN and GTH are groups, because connected components will have only one object, so they will just be groups. The connected components will be groups. Then this reduction is a group homomorphism, and it's kind of, well, it's important. So
will it be a groupoid homomorphism?
So in principle, well, a groupoid homomorphism is a functor, right?
Exactly.
So yeah, unfortunately, yeah, well, something can be said, but not. So you see, the problem is that GTN is a set of morphisms whose target is n. So they may have different sources, same target but different sources. And see, I mean, something can be formulated, but it can be tricky because see, n may be isolated, and H may not be isolated. So it's possible that, yeah, if you have a GT shadow with the target n, then the source is also n. But if you look at H, a GT shadow may have target H, but the source may be different from H. So it's like, imagine a Galois extension, finite Galois extension, and then inside that sequence, inside that two sub-extensions that are not Galois, and then a morphism, morphism between them. So it's like that. So yeah, so let's it makes sense to say a few words about GT hat versus, so how they are connected, this group to the groupoid. And well, so one relation is kind of straightforward. Given an element in GT hat and an N in NFI, we can form this pair. We can form this pair where this P subscript K denotes the standard continuous homomorphism from GT hat to G quotient by K. So, I mean, in order to understand details, you need to be fluent with profinite completions, but it's kind of, GT hat is basically built out of finite quotients like this. Therefore, we have, you always have this standard continuous homomorphism for every finite index subgroup. And that's what we do here. So whenever you have M hat, you can get a corresponding element in this quotient. And whenever you have a little F hat, you can have an element in this finite group. That's what I do. That's what I do. And it turns out that this is always a GT shadow with a target N. Always. So when you looked at, it's possible that when you looked at the definition of GT shadows, it's possible that these conditions were unnatural, right? It looks like they fall from the sky, right? But I mean, they're natural. They actually, I mean, they're related to the corresponding conditions, defining conditions for GT hat, and they're all satisfied. They're all satisfied. So yeah, then it makes sense to say that this element is this GT shadow is an approximation of the actual element of GT hat. And then, so a GT shadow is called genuine if there exists an actual element in GT hat such that its approximation for level n. For level n is that GT shadow. Otherwise, the GT shadow is called fake. And then, we say that a GT shadow with a target n survives into K, with K sitting inside n, if it belongs to the image of this reduction homomorphism. So, and then one can prove that a GT shadow is genuine if and only if it survives into K for every K sitting inside N. So you can think of this. So see, one of the problems is with GT shadows is that I can't really say that they are approximations, because some of them may be fake. They may not be coming from any element in GT hat. But then if you start with a GT shadow and you can prove that it survives into every finite index subgroup inside N, that is genuine, and vice versa. So just to complete the story, it makes sense to mention this. I call it the mainline functor. Given K and N, let's assume that they're isolated objects of this groupoid, and K sits inside N. Then let me remind you that the reduction map was a homomorphism of groups. And then this assignment gives us a functor from functor. So on the level of objects, so N goes to this group, and whenever K sits inside N, I just send it to the reduction map. So I get a functor from the pole set of isolated elements to the category of finite groups. And one can prove that the limit of this functor is isomorphic to GT hat. Well, more precisely, the gentle version of GT hat. So that's kind of, if you want to go back from the groupoid to the group to GT hat, you take the limit. I still wanted to talk about the action of GT shadows on Child's drawings, because there are some interesting results. And yeah, let me recall that a child's drawing of degree D can be represented by a group homomorphism from F2 to SD. And let me use square brackets for the actual child's drawing. So it's like equivalence class. So, and then, so we say that a child's drawing represented by psi is subordinate to N, or N dominates child's drawing if I have this property. So remember, NF2 is F2 intersection with N. So this condition does not depend on the choice of the representative. And yeah, so I'm going to denote by the sum of N, the set of child's drawings subordinate to N. And I'm going to denote by the sum the category whose objects are elements of NFI. And then given K and N in NFI, the morphisms will simply be all functions from the set of child's drawings subordinate to N to the set of child's drawings subordinate to N. And yeah, so now I can act, and this is the, yeah, so this is the, let's say that I have K and N, two elements of my poset, and a GT shadow from K to N, a morphism from K to N. And let's say that psi is a homomorphism that represents a child's drawing subordinate to N. Okay, then this new homomorphism represents a child's drawing subordinate to K. And this assignment defines a contravariant functor, simply a cofunctor, from the groupoid of GT shadows to this category, the sum. So, and one can show that this action is compatible with the action of GT hat. So I'm not going to make a precise statement, but you can try to make an educated guess, and it will probably be correct. So yeah, I do need this condition of subordinate, and yeah, if it looks unnatural, then you can just go back to the beginning of the story when we had this child's drawings represented by Belly pairs. So remember that coefficients defining curve and a morphism sit in a Galois extension. So this choice of this finite Galois extension is like a choice of N that dominates the child's drawing. That's precisely that. And then, yeah. So here is what, here is the action. It's just, well, it's convenient to define it in terms of a functor from this category from this groupoid to the sum. And well, let me explain what can be proved right away, kind of straightforward properties of the action. So the action of the groupoid is compatible with the action of S3, the one I defined before. So this is where we need hexagons. So hexagons play a role here. And it implies that the passport of a child's drawing is invariant with respect to the action of the groupoid. And then, so then the action of GTA of the groupoid is compatible with the partial order. So, well, it's kind of, there is a natural partial order. So if you think in terms of coverings is one cover, it lies above another, so like covers another. So it's so if you represent your child's drawing using a finite index subgroups of F2, then here is the condition that that one child's drawing is less or equal than the other if there exists an element in F2 such that this condition is satisfied. And the action is compatible with this partial order, which is helpful because I'm going to say that the child's drawing is Galois. So if so if the child's drawing is Galois, then so is the new child's drawing. And by Galois, it simply means that the corresponding covering is Galois or normal. And then, the action of GT shadows commute with operations of taking Galois closure. And finally, if a child's drawing is abelian, then the orbit is a singleton. So yeah, so all these properties can be proved. I mean, it's not hard to prove them using GQ. So if you want to talk about the action of GQ, and you can prove everything. But the amazing thing is that that I can prove this with just basic tools, just using group homomorphisms, group actions. That's all. Well, so now, yeah, let me tell you something that I think it's interesting. So, like,
Vasily, excuse me, it's so very interesting. But do you keep track of time?
Yes. Can I take 3 more minutes, or it's?
Sure, absolutely. Yeah.
Okay.
Go ahead.
Yes. So, so GT shadows. Well, here's a specific example, a concrete example. Let's take this family of dihedral groups, and this formula defines a homomorphism from PB3 to dn cross dn cross dn 3 times. And it turns out that the kernel of this homomorphism is normal in B3. Therefore, it's an element of my poset. And let me denote like this the dihedral. I'm going to call this the dihedral subposet. Dihedral subposet. And here is what we can prove about connected components of elements of this poset. So for every n, Kn is isolated. Hence, this is a finite group. And therefore, the Galois-Childs drawing represented by this admits a Belli pair defined over Q. So this is non-trivial. It requires some non-trivial things. And another thing is that this, if Q and N are odd, greater or equal than 3, and Q divides N, then this reduction map is on 2. Which means that if you try to use this poset to find fake GT shadows, you probably won't succeed. And finally, if you look only at odd values of N, then you get a functor. And the limit of this functor can be computed explicitly. Well, and I wanted to make this joke especially because Sasha is also here, I'm going to connect the joke to Sasha. So this is kind of interesting because using this poset, the first thing I saw was Child's drawings related to Chebyshev polynomials. I mean, actually, correct pronunciation is probably Chebyshev. And it turns out that Pafnuty Chebyshev is my distant mathematical ancestor, and same for Sasha.
Wow.
So, I mean,
I didn't know.
You didn't know that?
No.
Okay. Well, of course, it goes through Yuri Manin.
And Shaparevich, I suppose.
Yeah.
Oh.
Okay. So this is straightforward with, this story is kind of easy. I mean, it's just, here it's straightforward to show that GQ orbits are singletons. But this is a bit more interesting. It requires more work. And this example requires even more work, but it can be done. So basically, using GT shadows, you can show that this family of Child's drawings, the GQ orbits of these Child's drawings are singletons. Well, and since I'm kind of short on time, let me just formulate properties of this family of Child's drawings. That the degree of Cn is 2n squared. Cn is not Galois. Cn is subordinate to Kn, and the orbit of Cn is a singleton. Therefore, the orbit of the GQ action is also a singleton. And well, for a specific example, n equals 3. C3 is represented by this permutation pair. And its passport is given here, its genus is 2. So Well, one more thing I wanted to mention. I'm actually finishing. I'm finishing my talk. So I wanted to conclude it with acknowledgement to collaborators that thank you for working with me. So this, Jacob and Jessica were undergraduate students, and now they are graduate students. And Jingfeng Xia is currently a PhD student at Temple University. And if you're interested, and if you're an adult mathematician, for example, like Sasha, who shares the same mathematical ancestor with me, so he's a natural candidate. So thank you.
Thank you, Vasily. Thank you, Vasily. Any questions? Or comments? Well, if nobody comes up with a question, I can ask. I wanted to ask one. Is it with those GT shadows? Is it easier to deal with the relation with the actual Galois group, GQ?
Yeah. So so in principle, it's well, that's what. Yeah, I gave a version of this talk recently at UPenn. And I mean, there are many people there who worked on this, and so they understand a lot. And they kind of keep asking me similar question. They keep asking me, so can you use GG shadows to say tell something about GQ?
Right. Yeah.
So far, my approach is kind of opposite to Kennedy's. Like Kennedy's famous saying that. Don't ask what you can do for GQ. I mean, so I'm kind of doing the opposite. Don't ask what you can do for the country. I mean, I'm asking the opposite question so far. How can I use GQ to say something about GT shadows? For example, produce genuine GT shadows in a non-abelian setting. So I think it's something that can be done. It can be done. But kind of in the opposite direction, I'm not sure yet. I'm not sure, but it's possible.
Okay. Thank you. Other questions? Well, if not, let's ask Vasily for the very interesting talk again.
Thank you. I'll stop recording.
Sure. Yeah. And I'll stay here for